Welcome to the first lecture of the Origin Science Scholars Program at Case Western Reserve University and the Cleveland Museum of Natural History, organized by the Institute for the Science of Origins with the assistance of CWRU's College of Arts and Sciences and the generous support of Richard Morrison. The series is an introduction for the public to cutting-edge origin science. My name is Glenn Starkmann. I'm the director of the Institute for the Science of Origins, as well as a professor of physics here at Case Western Reserve University, and it just so happens the first speaker. So, we're going to start tonight with an introduction to cosmology. That's our first course, and tonight I'll be the speaker, and next week Evelyn Gates, director of the Museum of Natural History and a cosmologist herself, will be the speaker, followed in the third week by me coming back and telling you a little bit more about the very early universe. So it's an introduction to cosmology. We hope by the end that you'll understand a little bit more about the universe that we live in. So the first week we call the case for the Big Bang. And what I'd like to start to do is tell you that the universe is very, very big. I know you probably know that already, but we'll go into a little bit more detail than just that. Then we'll discuss the fact that the universe is expanding. We'll save the odd way that it's expanding for next week. Then the fact that the universe was once much hotter than it is right now. I don't know if you knew that the universe had a temperature, but it does, and it's quite cold. Once upon a time, it was a lot hotter. And we are able to measure the afterglow of the early period in the universe when the universe was much hotter, and that afterglow, we give a name. It's called the cosmic microwave background. Next week, the title of the talk is Almost Everything is Dark by Dr. Gates, and that's about dark matter and dark energy, and we'll round up the first 3-week part of our program with, in the beginning, talking about the smoothing and unsmoothing of the universe, how we make matter, and how we make the light elements in the early universe. Okay, well, so, as I said, the universe is very, very big. Well, how big? And how do we know? To get an idea of how big, we should start by realizing what our unit of measurement is. We're all used to measuring things in inches, feet, yards, miles. Where I come from in Canada, meters, kilometers. These are all lengths that we can all get our heads around. We know about how far a mile is. If I told you to go for a mile-long walk, you'd know to walk for about 20, 30 minutes. Well, it depends how fast you walk. But you wouldn't walk for 100 miles, and you wouldn't walk for 50 feet. You have a good idea of how big a mile is. We can't really measure the universe in miles because we'd use up our stock of zeros. So we devise a new unit, and that's called the light year. And it's based on the fact that light, and when I say the word light, I'm really including not just this stuff, this visible light that we see, but all sorts of other things like radio waves and microwaves and X-rays and gamma rays. These are all things that Maxwell, about 100 years ago, told us are all related. They're vibrations of the electromagnetic spectrum. They're forms of light. And they don't travel instantaneously from one place to another. They seem like they do. Right? Oops. And we'll see that in a second. It actually takes them time to get from A to B. So I'm going to play that recording for a minute again. This is a recording of the Apollo astronauts talking to Earth. And what you'll hear is someone saying something from mission control, and then the astronauts talking, and then listen closely to what you'll hear at the end. So let's do this. Play this again.
Picture here, I tell you. Come on a little bit closer.
Did you hear the echo? That echo took 2.7 seconds to make the round trip from here to the moon and back. Now, the moon is about 500,000 miles away, and that means that the speed of light is about 186,000 miles per second. That's really fast. But it's not instantaneous, and we can make measurements in the laboratory of that speed. Okay, so we know we can measure much more precisely than I've shown you there what the speed of light is. 186,000 miles per second, or about 300,000 kilometers per second. And that means that in 1 year, light travels about 6 trillion miles. Right? That's not a number we use very often, although nowadays it's much more common in reference to things like the national debt. Okay? So maybe we understand trillions now. Okay? But that's just 1 light year. Actually, the unit that astronomers use more than light years is something called the parsec, which is about 3¼ light years. And sometimes you'll hear me lapsing into the word parsec and just divide everything I say by 3. Sorry, multiply everything I say by 3 to get how many light years it is. I'll try to remember to do that. Okay, so now let's try to get an idea of if we're going to measure distances in units of how far light travels in a given time, how big things are. So here is something that you recognize. Here's the solar system. Not exactly the scale. Here's the sun rather big in the center. And then the various planets. Here we are out here on the Earth with our moon. So we said it was about 2.5 seconds round trip from the Earth to the moon. It is about 500 seconds from the sun to the Earth. In other words, it's the light that we are getting. If we go outside and feel the sunshine, that sunshine left the sun about 8 minutes ago. So the sun might have turned off 8 minutes ago, and we wouldn't know it. Okay? It's not very likely. We don't expect the sun to turn off for a few more billion years. But it might have, and we'll know in about 8 minutes. Okay? In fact, it takes light about 4 hours to cross the solar system, from the sun to Neptune, the inner solar system of the planets. If you still count Pluto, it takes about 6 hours sometimes when Pluto's far away, and about 4 hours when it's nearby. Okay? How do we know this? We can't go out there with our yardsticks or our tape measures or any of our usual ways of making measurements on Earth to tell the distance to a planet. Well, nowadays, the way we do it is by first measuring the speed of light on the Earth. Okay? And then we can measure the time it takes for a signal to get from one of our distant spacecraft that went out to one of these distant planets. And we can measure how long it takes for a signal to get from that spacecraft to here. Those spacecraft have very accurate clocks on them, for example, and it can send out a signal and say, it's 6 o'clock, and then we can wait and see what time do we get that signal. And if it's at 9 o'clock, then we know that the spacecraft is 3 light hours away. The other thing we can do is we can actually shoot radar beams at some of the nearby planets, like Venus and the Moon. And we can measure the distance to nearby planets by radar ranging, the same way the police catch you speeding. So the scale of the solar system is a few light hours. Now, one of the things that makes you realize is that since the speed of light isn't infinite, since light doesn't travel instantaneously from one place to another, but at a finite speed, when we're looking out in space, we're also looking back in time. So we're seeing things as they used to be. When we look at Jupiter, okay, we're seeing Jupiter as it was a couple of hours ago. When we're looking at the sun, we're seeing the sun as it was 8 minutes ago. Okay. When we look out at the night sky, we'll see something like this. Well, not from downtown Cleveland, we won't. But if we went out somewhere very dark, we would see lots and lots of stars. People think we'd see billions and billions of stars. They remember Carl Sagan saying that. We don't see billions and billions of stars unless you have very, very good eyes, much better than any human alive. You see a few thousand stars if you have very good vision. Now, that's a few thousand individual stars. We'll see bright objects in the sky that are little blobs. Those are other galaxies, and they have billions and billions of stars. So we can see billions and billions of stars, but not individually. We can only count a few thousand stars. those stars are, most of them, within about 50 or 60 light years. So you're seeing them as they were 50, anywhere from 4.25 years ago for the nearest star, called Alpha Centauri Proxima. That's the nearest star to Earth, to, 50, 60 years ago. The most distant visible star is a star called S Carinae, and it is 12,000 light years away. Okay? So when we look at that star, we're looking at it as it was about 12,000 years ago. So the things in the night sky, the stars in the night sky, are a few light years away from us, typically. Okay. How do we know how far a star is? Well, actually, it's exactly the same way that you can tell how far away I am from you. Right? If you put your hand over one eye, you can go ahead and do that. Put your hand over your right eye, okay, and look at me, and then without moving your head, switch it to your left eye, and you'll notice that I move a little bit. Right? As we look at things from one eye to the other, we'll notice that nearby objects tend to move on the sky. That's something called parallax, and the fact that our two eyes are looking from slightly different directions and see things in slightly different directions allows us to tell how far away something is. We can do the same thing using the motion of the Earth. So let's see. Now I've tried to make all of these little movies, things that you can access on the web very easily, and I put the links up there on the PowerPoint, and of course this one decided not to work. I don't know. Oh, here we go. Okay. So here we have the sun, and the Earth is going to go around the sun, and here's some star, and here are lots of distant stars over here, and this is what you'd see looking from the Earth. So let's look at what happens to the positions of those stars looking from the Earth. Notice that they move a little bit on the sky. And notice that this red one, this nearby one, moves the most. Okay? So as the Earth goes around the sun, the stars appear to move a little bit on the sky. Okay? And the farther away the star is, the less it moves. So by measuring how much stars move on the sky, we're able to tell how far away they are. Okay? Now, that doesn't work for very many stars. There's a satellite that was launched a number of years ago called the Hip Arco Satellite. It did this measurement of the distance of stars for about the nearest 100,000 stars. And it did it very, very accurately. So the nearest 100,000 stars, we're able to measure their distance using their apparent motion on the sky due to the motion of the Earth around the sun. Okay. So now we're getting out relatively, kind of a little bit further in our galaxy. The nearest 100,000 stars, they're all within about 100 light years of us, a little bit less. Okay. This should look familiar. It looks a lot like our galaxy, the Milky Way galaxy. We live in a galaxy that we think looks very, very much like this. In other words, if you were able to leave our galaxy, which is hard because you'd have to take a trip, this is probably taken from maybe a couple of 100,000 light years away. So moving at the speed of light in your rocket ship, if you went for a couple of 100,000 years, turned around and took a picture of the Milky Way, this is about what it would look like. And we would live, we would live somewhere, in kind of some nondescript place like that. Okay. Nowhere special, not near the center, which is a good thing. It's probably not such a great place to live, a lot of X-rays. Somewhere a kind of 2/3 of the way out on on a spiral arm. Okay. So this galaxy has a size of about 100,000 light years. Okay? So it takes light about 100,000 years to get from here to here. To get from the center of the galaxy to us takes about 25,000 years. Okay? So we can look up in the night sky, and we can see the center of the galaxy, and that light from there, from the black, for example, from the black hole at the center of the galaxy, is coming to us on a trip of about 25,000 years. So we're seeing the center of the galaxy as it was 25,000 years ago, before there were cities or much human civilization. So we know that there are many, many galaxies, about 100 billion to a trillion galaxies out there. And many of them look like this. Many of them are more kind of amorphous. Some of them are nice and elliptical. Here is our nearest big neighbor. It's called the Andromeda Galaxy. So this is really in our neighborhood in the universe. This galaxy is about 2 million light years away. We're finally now starting to get out to the scale where we're really talking about the universe and not about individual objects in the universe. This is a cluster of galaxies called Abell 1689. And it is about a few million light years across. And finally, let me show you this picture. This is called the Hubble Space Telescope Ultra Deep Field. It is a small piece of the sky, smaller than occupying an area significantly smaller than the moon. Okay, so a very small piece of sky that the Hubble Space Telescope was directed at whenever it had free time for many, many, many hours. Okay? And you can see thousands and thousands, actually more than that, of galaxies here, okay, of all sorts. You can see spiral galaxies and elliptical galaxies, and there's also stars in the foreground, all sorts of objects, and a whole lot has been learned by studying the objects in this deep field. Okay. So we've now taken a tour of the universe from our solar system where the scale is, or from the Earth-Moon distance where the scale is about a second, to the solar system where the scale is several hours, and now we're out to a distance where light is taking about the age of the universe, about 10 billion years to get from those galaxies to us. Not quite 10 billion, a few billion years. So how do we know how far away things are that are that far? We can't use parallax. Remember, that was the last thing we talked about, using parallax, using the motion of the Earth around the sun to give us stereoscopic vision and tell us how far away the nearest 100,000 stars are. But that is not going to tell us how far away a galaxy is whose light is coming to us from a few billion light years. Okay? It's not even going to tell us how far away a galaxy is that is in that Abell 1689 cluster. Okay? To do that, we have to have what are called standard candles. What's a standard candle? Well, it's just what it says. Imagine that you had a candle, a box of candles. You know that if you took a box of candles and you lit one, it would give some light. You could put it out. If you took the next one, it would give a slightly different amount of light. And if you took all the candles in that box, unless someone's taken an inordinate amount of care in making that box of candles, they're all going to be a little bit different. Right? Well, if we look at stars, they aren't all the same brightness. But there are certain types of stars whose brightness is the same, or at least whose brightness we can know without measuring it. Without measuring the brightness of that star, we can tell how bright that star actually is. For example, there's a kind of star called a Cepheid variable. This is a star that during its life puffs up and shrinks down, puffs up and shrinks down periodically. And that period, it turns out that if you know how often it does that, you can tell exactly how bright that star is. So once you know the period of the star, once you know the rate at which it gets brighter and dimmer, you know exactly how bright that star is. Now, if you have a star like that, something that you know exactly how bright it is, and you put it far away, then it's going to appear dimmer. The further away you put it, the dimmer it will appear. So imagine that I took now a box of really well-made candles, all of which were exactly the same, and I put one close, and one twice as far, and one 4 times as far. Then you could, if you looked at those candles, you could say, well, that one is twice as far because I'm getting only a quarter as much light from it. So I could look at the candles and say, I know how far away that candle is by how much light I'm getting from it. Okay? But you have to have a really well-made box of candles. And the Cepheid variables are our best box of nearby candles. Okay? They have been very well calibrated now so that we know very well exactly how far away a Cepheid is once we see it. So they allow us to measure the distances to many, many galaxies. Now the problem is there's not a huge number of Cepheid variable stars. This takes us out to something like 10 million light years. Beyond that, probably the best standard candle, although there are others, are a type of supernova called type 1a supernovae. Okay? You know what a supernova is? It's a star that explodes. Okay? And as you can imagine, you would expect that different stars are going to explode with different brightnesses, depending on the detailed properties of that star. And for most supernovae, that's true. We can't predict exactly how bright different type a supernova is going to be. However, there's one type of supernova that comes from slowly dripping material onto something called a white dwarf. A white dwarf is a dead star like our sun. Our sun will one day turn into a white dwarf. Long, long time from now. Don't worry about it. Not 8 minutes from now. A few billion years from now. Okay? It's a dead star. Okay? And if you start pouring material slowly onto that star from a companion star that's orbiting around it, then eventually that star will reach a critical point where it has too much mass sitting on top of it, and it'll collapse and then blow up as a supernova. Okay? And that is called a type 1a supernova, and they are essentially all the same brightness. So we can use those as standard candles, because if we know how bright that supernova is, and we look at it and see how bright it appears, we can tell how far away it is. And this is one of our best ways of measuring the distances to these very distant galaxies. Okay, so we use standard candles. So now we know that the universe is very big. The size of the universe is such that light takes billions of years to get across the universe. And remember, a light year was 6 trillion miles. So we're talking about 60 billion trillion miles across. And now you know why we don't use miles, because we really would run out of zeros. We'd fill our paper with zeros. Okay, so the next thing I'd like to tell you is that the universe not only is big, but it's actually expanding. Well, how fast is it expanding, and into what? And how do we know it's expanding? So let's come back to that Hubble Ultra Deep Field. Actually, here's a picture of it with, you can see this red box. Here's the moon on the sky, how big the moon would appear. And here's this Hubble Ultra Deep Field. Okay. And we can look at the galaxies, and here is that field blown up. So we take a little region of the sky about that size and look at it for a long, long time with the Hubble Space Telescope. And we can look at all the galaxies in that, and we can tell how far away, we can tell not just how far away some of them are, but we can also tell how fast they're moving away from us or towards us. How do we do that? Well, we use something called redshift. So if we're looking at some source of light, if we're looking at some source of light, then depending on whether it's moving towards us or away from us, it will actually change color. And I have a little tiny movie here that we can play. Okay. So, all right. So here we have a yellow object. And when that object's at rest, it looks yellow. So this could be like a distance, like our sun seen from far away. But if the object is moving towards us, it will appear a little green. And if it's moving away from us, let's go. It'll appear orange. Okay? So things that are moving towards us appear, yellow starts to appear a little green, then blue. if it's moving towards us. If it's moving away from us, it appears a little orange, and if it's fast enough, a little red. So objects that are moving towards us appear bluer. Objects that are moving away from us appear redder. Now, you'll never see this on in an ordinary walking around. You'll never see something yellow all of a sudden start to appear blue because it's moving towards you. Because to do that, it would have to be moving close to the speed of light. Okay? It would have to be moving very, very fast for its color to visibly change to us. We do see this. Notice the same thing though with sound. So if you're ever standing beside a road and you listen to the cars pass by, then as the car passes by towards you, it kind of has a high sound, and then as it goes by you, away from you, it has a low sound, kind of like, ooh. That's the same effect for sound. So sounds moving towards you appear higher, kind of that's bluer. Sounds moving away from sources of sound moving away from you appear lower. That's like redder. So the same thing is true in light. This is called the Doppler effect. Oops. Okay. So the Doppler effect works in such a way that if galaxies are moving away from us, then they will appear a little bit redder. And the faster they're moving away from us, the redder they appear. Okay. Now, we might expect that if we look out at galaxies that some of them would be moving towards us and some of them would be moving away from us. But actually, when we look out at these really far galaxies in this ultra-deep field, we find that they're all moving away from us. Every single one of them. How can that be? Well, in fact, when we look at any galaxies that are more than a few million light years away from us, more than, say, 10 million light years away from us, they're all moving away from us. So galaxies nearby us could be moving toward us. Andromeda, for example, is moving toward us and will hit us, in a million years or so. But distant galaxies, they are all moving away from us. And the farther they are, the faster they're moving away from us. It's, in fact, a linear relationship. So if you double the distance to the galaxy, then it's moving away twice as fast. And we can actually, people spend a lot of time measuring the slope of this line. The person who discovered this relationship is Edwin Hubble, the guy who got the telescope named after him, in part for discovering this relationship. He got the slope completely wrong by about a factor of 7 because he was actually looking at galaxies that were much too close. But anyway, he discovered, he got lucky. He discovered this relationship, which is rather remarkable. So we write that v, the speed or the velocity of a galaxy, is proportional to the distance away, r, and the slope of that line, this is one of the few pieces of math we'll do, is called h, the Hubble constant, named after Hubble. And its value is about 72 kilometers per second per megaparsec. That's a lot of words. What does that mean? It means that if something is 10 megaparsecs away, that's about 30 million light years away, then it'll be moving away from us at about 500 miles per second. That's pretty fast. If it's 10 times further away, it'll be moving away from us 10 times faster. Okay? So objects, the further they are away from us, the faster they're moving away from us. And from this, we learn that galaxies are receding, and so we have two choices. Okay? We can imagine, so no matter everywhere we look around us, the galaxies are moving away from us. How could that be? Well, it could be that kind of like actors on a stage running away from the center of the stage, or the shrapnel of a big explosion that happened long ago. And that's what probably most people think about when we say the Big Bang. Right? I imagine that when I say the Big Bang, you think of something like this. So that was a rocket. No one got hurt there. That was a rocket that accidentally exploded. But what you see is all this fiery shrapnel moving away from the center of the explosion. Right? And that's what most people think about when we say the Big Bang. Okay? So there's space out there. somewhere there was an explosion and all the debris, which is us, the galaxies, went flying away from the center of the explosion. Okay. The other possibility, and the one that turns out that we think is actually right, is that it's not that stuff was sitting there and all of a sudden exploded, but rather that space itself is expanding and carrying everything with it. Okay. So let me try to give a demonstration of that. And this is a standard demonstration that all cosmologists are required to do. Okay. So we come equipped with balloons. When we get our degrees, they issue us a large quantity of balloons and markers on which we put little dots. Okay, so here are some little dots, and you can imagine that we are living on one of these little dots. It's called the Milky Way galaxy, and here are some other galaxies out there. Now, pretend that you're sitting on this dot. That's the Milky Way galaxy. We'll make it look nice. Here, there's a nice Milky Way galaxy. Okay, nice spiral galaxy. And you're looking out and you see all these other galaxies. And now some time goes by and the universe expands. In this case, the Milky Way galaxy got bigger. That doesn't actually happen. But notice that all of the other dots move farther away. But the thing is, no matter if you had lived on this galaxy, let's suppose now that we go back and imagine that we live on some other galaxy, not the Milky Way. We'll circle it with a nice red circle. So here we are living on this galaxy now. The universe expands, and notice that all the other galaxies moved away from that one too. That's really different than the explosion, right? So what we think is that it's more like the surface of this balloon, where no matter which galaxy we happen to live in, we live in the Milky Way, but we could have lived in some other distant galaxy. If we looked out around us, we would look in all directions and see the galaxies moving away from us. Now, why do we think that's true? It doesn't have to be true. It could be like the other picture. But our theory of gravity, which was developed by Einstein back in 1916, or at least completed by him in 1916, called general relativity, tells us that space responds to the presence of matter in it. When we have massive objects like galaxies, it does things like bend space. And space, when we fill space with lots of galaxies, it ends up having kind of two choices. It can expand or it can contract. Now, Einstein didn't like that, and he invented something called the cosmological constant in order to carefully balance things so that the tendency of the universe to expand or contract could be balanced against this extra force that he created with this cosmological constant. But we know that it is virtually impossible to balance it in that way. It's an unstable balancing. It's like trying to balance a pencil on its tip. You can do it for a little bit, but eventually it falls over. In the same way, that balancing act doesn't seem to work. The universe, if it's described by Einstein's theory of gravity, has two choices: expand or contract. And our universe seems to be expanding, which is a good thing because that gives us a lot longer to live in it. If it was contracting, it eventually would end in a big crunch. Okay. So space seems to be expanding. Now, we still tend to have a picture of that looks something like this. So almost certainly misleading impression of things moving away from this one center and that we live in this center. So let me emphasize, we don't think that we live in any particularly special place. I can't prove to you that we don't, but it's incredibly unlikely that we live precisely at the center of the universe. It's much more likely that we live at a very ordinary place in the universe, and the universe is such that no matter where you are in the universe, everything is moving away from you. Okay? So what is it expanding into? Well, one possibility is that our universe is a region in a larger space, and only our piece is expanding. That's the picture we tend to have. And if you ask me what is it expanding into, what we tend to think of is that there is some space out there, and here's the universe, and the universe is going to expand into that space. That is one possibility. Another possibility is kind of like this balloon. So this balloon is a surface, a two-dimensional surface. An ant could walk around on this balloon and never know about the world off the balloon. And in order to expand, the balloon has to occupy more, it has to move out into space. It could be that we are kind of like living on the surface of a giant balloon, except it's a three-dimensional balloon, moving out into a space that has even more dimensions than we have. Okay? But it turns out that the simplest explanation is actually that our universe is all there is, and space just expands. Now that's, I know, very, very hard to imagine. So instead, what you can imagine is that space isn't expanding at all. You're just shrinking. Now it turns out that that is a perfectly good way to describe what we see. We don't like that because we don't feel like we're shrinking. But I'm talking about us shrinking relative to the distance to the nearest galaxy by, if you are about, let me use meters, if you're 2 meters tall, you would shrink by 2 centimeters every 100 million years or so. Has anyone noticed if they've shrunk 2 centimeters the last 100 million years? So we wouldn't notice. And in fact, the thing is we couldn't actually tell the difference. So you can think, if you like, of the universe expanding and us staying the same. Or you can think, if you like, about the universe staying the same and everything in it shrinking. But one way or another, the simplest explanation is that all there is our universe, and space is just expanding in it. Okay. By the way, not only is space getting bigger, it's getting bigger faster. And join us next week when Evelyn Gates will talk about that and talk about dark energy. Okay. So part 3. Not only is space getting bigger, it's getting colder. So it turns out that when we expand things, we make them cool. Probably many of you have used a bicycle pump or used a pump at the gas station to fill up your tire. Have you ever noticed that the end of the pump gets really cold when the air comes out of it? That's because as the gas expands out of the end of that pump, it actually cools. When gases expand, they get colder. There's a wonderful photo of that here. This is a U.S. Navy jet breaking the sound barrier. And as it breaks the sound barrier, it causes the expansion of some of the air behind it. And if it's just the right conditions, you get a cloud forming, you get condensation. So we see this effect of expansion causing cooling. Now, here's a brilliant observation. If the universe is getting colder, then it used to be hotter. So imagine rolling back the universe in time. So right now the universe is cold. I'll tell you how cold in a little bit. And roll back the story, turn time backwards, and the universe used to be hotter. What was happening? The matter was the stars were getting closer and closer together. The galaxies were getting closer and closer together. Everything was nearly on top of each other. Everything was getting hotter. In fact, it was about this hot, about as hot as the surface of the sun. When the universe was about 400,000 years old, today it's about 13.5 billion years old. When it was about 400,000 years old, it was about 1,000 times smaller and about 1,000 times hotter, and it was about as hot as the surface of the sun. Okay? At that point, all of the atoms in the universe would get stripped of their electrons. Okay? So you'd have what's called a plasma, just like the surface of the sun. And if you ever notice, if you try to look at the surface of the sun, don't do this at home, you'll hurt yourself, it's opaque. You can't see through the sun. Why is that? Light coming through, if we shone a light at the sun, okay, it would hit the sun, and it would hit some of the electrons in the sun and start to scatter around in the sun. Actually, it's just as easy to do that with a piece of metal, for example, which is in many ways very similar. You have lots of free electrons running around in the metal, and you can't see through the metal, as opposed to being able to see through the glass. Okay? So the universe used to be, like the sun, hot and opaque. Light couldn't get through it. And then, now let's run the movie forward, the universe started to expand, and as it expanded, started to cool, and all of those electrons running around, they got together with protons and with nuclei, and the universe became transparent relatively quickly, over just a few thousand years. Okay? The universe went from being opaque to being transparent. And that means that the light, that light that was bouncing around in the universe when it was hot like this, like the surface of the sun, all of a sudden says, oops, there's nothing to bump into. And it starts traveling through the universe. And it's been traveling through the universe for the last 13.5 billion years. Okay? So here's kind of a picture of what that journey is like. Here it is. We can imagine somewhere way out here, the universe being opaque. Remember, as we look out, here's the Earth. As we look out in space, in space, we look back in time. So imagine we're looking back here to a time when the universe was about 3,000 degrees. About 3,000 degrees centigrade, about 5,000 degrees Fahrenheit. Okay? And the universe is hot and opaque, and then it becomes transparent, and the light comes traveling through. It passes all sorts of galaxies, and then it passes neighboring stars, and eventually it comes to us in the Earth. Okay? So we can look out in any direction, and we can see this light coming to us from when the universe was just about 400,000 years old, was about 1,000 times denser, 1,000 times smaller, about 1,000 times hotter, about as hot as the surface of the sun. And we can actually measure that light. We can measure that afterglow. Now, you should be worried at this point, because I just told you that there's light coming to us from when the universe was about the temperature of the surface of the sun. So that means that when we go outside, you should expect that there is like a heat lamp from the early universe that's about the temperature of the surface of the sun, the light coming from everywhere. We should get a horrible sunburn, right? Because it would be like every place in the sky is just as hot as the sun. Imagine that the sun filled the entire sky. Imagine how hot it would be on the Earth. Now, the good news is that in the meantime, the universe has been expanding. And as it's expanded, it actually has stretched the light. Okay? It's made the wavelength of the light longer, and so it's made it redder, and it's made it much cooler, much lower energy. In fact, that light, instead of being the color of the surface of the sun, is very, 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 very red. How red? It's actually about the same as the microwaves in your microwave oven. Okay? So instead of coming to us as bright visible light, it comes to us as microwaves. And that means that we can't use our eyes to see it. We have to use a giant dish like this one. This was actually the first dish that was with which the microwave background was seen. It was seen by two Bell Lab microwave engineers in 1964 and 5. Their names were Arno Penzias and Robert Wilson. They weren't looking for this. They were just trying to build a better microwave telescope. And they scooped the team at Princeton that was building an experiment trying to look for this. And for this work, they won the 1978 Nobel Prize in Physics for seeing this, the night sky in microwaves. So everywhere you look at the night sky, you would see a glow in microwaves. You can actually, well, I don't know if you can still see it yourself. You used to be able to see this yourself on your television if you turned to a television station that was off station. You know, you got that fuzz. About 10% of that apparently is this radiation. So you are actually detecting it when you look at the fuzz on your television. Today it's probably a lot noisier than that. So the temperature of this radiation now is like something glowing at the wonderfully hot temperature of about 3 degrees above absolute zero. This is incredibly cold. This is much cold. This is colder than ice. It's colder than liquid nitrogen. It's colder than liquid helium. It is very, very, very cold. Only the most sophisticated laboratories on Earth are able to produce temperatures this low in the laboratory. Actually, at this point, lots of places can make things about this temperature. But you're not going to get it in a commercial refrigerator. So, but nevertheless, this is the remnant glow of the early universe. And we can detect it with antennas like this. Okay? Now, nowadays, actually, our antennas look... to remind you, so what we're seeing is this light coming from the early universe, when the universe was just a few 100,000 years old and went from being about the temperature of the surface of the sun and opaque to all of a sudden being transparent and us being able to travel through the universe. Now, the thing about that is, notice how smooth this is. It's the same temperature in every direction. Here I've portrayed that as the same color in every direction. Amazingly so, to 1 part in about 100,000. Okay, so the temperature variations are millionths of a degree. Okay? And that's kind of surprising because if you'll notice, there's all sorts of things in the middle. The universe isn't that smooth. The universe is actually pretty lumpy. After all, we're here. Right? The Earth is here. The Sun is here. Our galaxy is here. There are big lumps in the universe, and we would think that those would get reflected in this light, that we would see those in the light that we see from this microwave light that we see from every direction on the sky. And for a long time, we couldn't see it. It took until the early 1990s, and we had to launch a satellite to do it. It's called the Cosmic Background Explorer. And finally, after 25 years of looking for inhomogeneities, for differences in temperature from one place to another, they were able to measure this. Well, this looks the same. Well, actually, they were able to measure this, make a map that looks like this. This is actually just due to the fact that because the Earth moves through the universe, we're able to tell that we're going this way. Okay? This way. Because as we move towards the light, it looks a little bluer. As we move away from it, it looks a little redder. Okay? But finally, they were able to understand all of that and measure these tiny, tiny differences of just 18 millionths of a degree of temperature between one place and another on the sky. So the temperature of the sky is different in different directions by millionths of a degree. Now, that doesn't sound very exciting. That sounds pretty boring. Until I tell you that you came out of one of those. The only reason that you and I are here is because of this. These places that are cold are places where there was more stuff. Okay? And so the gravity was a little stronger, and so the light had a little bit harder time in climbing out of the gravity and getting to us. Well, as time went on, those places where there was more stuff attracted still more stuff. Okay, so it started off as very gentle ripples, a little bit more matter. And then after a while, some more stuff fell on it, and some more stuff fell on it, and some more stuff fell on it. And eventually those things turned into first galaxies and then clusters of galaxies. And the galaxies turned into stars and planets. So we're literally seeing where we came from in these patterns. So that was in the early 1990s. Since then, we've done things like send balloons up from the South Pole to measure the more detailed properties of that. And actually, this experiment was led, at least for part of the time, by a professor here at Case Western called the Boomerang Experiment. And now there's also another satellite up there called the Wilkinson Microwave Anisotropy Probe. And instead of making a map that looks like this, kind of shoddy looking, a little bit what we call low-resolution map, it is able to make a map that looks like this. So it's able to measure all the very fine structure in the universe. Okay? It's able to look out and see all of the incredible properties of the universe. And this is one of our most fantastic windows on the universe. Okay. We can look at this map and we can tell where there are clusters of galaxies forming. We can look at and we can actually use this map to learn about what the universe was like, not when it was 400,000 years old, but what it was like when it was much less than a second old, too. Because, as we'll talk about in week 3, the way that this pattern came about was determined at the very, very beginning of the universe, when the universe was probably less than a billionth of a billionth of a billionth of a billionth of a second old. So our fate is readable here, but was written a tiny fraction of a second after the Big Bang. Now, this map has really changed the science of cosmology, okay, in ways that are hard for cosmologists to believe and maybe hard to understand. So, before this map, and to some extent its predecessor, this map, people like me, theoretical cosmologists, could come up with crazy ideas, confident that no one was going to be able to tell us they were wrong. And that's really a lot of fun. It's great to be able to play in that way. Theoretical physicists like to do that. They like to come up with ideas that they know in principle could be tested, but 20 years from now, by that point, you could be a famous professor with lots of students. You can win some awards, but no one will have shown that you were wrong. That's what cosmology was in many ways like until this map, and really until this map. So this map told us that apparently some of our important ideas about cosmology are right. Okay. It told us, for example, that probably only about 5% of the energy in the universe is made of ordinary stuff like that. That is very, very strange. We thought, if you had asked a cosmologist 50 years ago what the universe was made of, they would have told you, well, it's made of, the stuff in the universe is made of protons and neutrons and electrons, just like everyone learns, in chemistry class. It's the same stuff as in chemistry. That's what the universe is made of. Because that's what stars are made of, and that's what planets are made of. It's made of ordinary stuff. Well, after a while, if you had talked to, maybe by the 1960s and 70s, certainly, they would have told you, well, some of the stuff is this, but a lot of it is something else. It's called dark matter. And what's dark matter? It's stuff you can't see. Okay? It's a lot like ordinary matter, but you can't see it. Well, what is it? It could be things that are just like Jupiter. Lots and lots of Jupiters out there. Well, we've looked for Jupiters. We don't see Jupiters. It could be black holes. Turns out black holes, it's very hard to make that many black holes. And we've looked for enough black holes. There aren't enough black holes. There's only about 1/1000th as much matter in black holes, 1/10,000th maybe, as you would need. So it's not black holes. What is it? Well, we're not really sure. We have some ideas. Particle physicists were out there making up theories that said that there would be new particles that have wonderful names like photinos and supersymmetric particles and axions and WIMPs. And they're massive things 30 to 100 times more massive than protons. And the main property, their main virtue is they're very hard to see. In fact, if this theory is right, that this is what the dark matter is, there are billions of them going through my hand right now. And yours. Okay? And they don't do anything to it. And what we have to do to find it is we have to build detectors, very, very sensitive microphones or thermometers, stick them at the bottom of deep mines, with very, very precise instrumentation and then sit there for a year and hope that maybe 10, 20 of those dark matter particles will hit the particles in our detectors, in our microphones or thermometers. And people do that. There's a program over the last 20 years to build these detectors, and they're now getting up to the size of a ton. Hundreds of kilogram detectors sitting at the bottom of mines in South Dakota and in northern Ontario and under the Alps in Italy and deep in the Himalayas in China. Okay? But this map tells us not only is this true that most of the galaxy is not made of ordinary matter, maybe only 20% is ordinary matter, but in fact, most of the energy in the universe is neither ordinary matter nor this dark matter, but something else, something that we call dark energy. Okay, what's dark energy? We don't know what dark energy is. But Evelyn Gates is going to tell you a lot about it next week, or at least a lot about how we're looking for it, because it is really, really strange stuff if it exists. It's strange because instead of pulling on things like with gravity, dark matter and ordinary matter have the property that you take any two pieces of matter, dark or ordinary, and put them side by side, and they'll pull on each other because of gravity. The Earth is pulled to the sun by gravity. The sun is pulled to the galaxy. All the galaxies are held together by gravity. This stuff pushes apart, and is causing the universe to expand faster and faster and faster with time. Okay? In a way that is completely surprising, and that we've only really been able to measure over the last 15 years. Okay. So WMAP has told us this sky, as measured by the Wilkinson microwave anisotropy probe, has told us and continues to tell us that many of the things that we are thinking about our universe that are very strange seem to be right. But it's also shown us some mysteries. And I hope to tell you a little bit about those mysteries in week 3, some things that maybe we don't understand. And the search goes on because we'd really like to be able to explore this visible universe. This is all we're ever going to see of the universe. Here we are sitting at the Earth, and light has been coming to us since the beginning of time, since the origin of the universe. And really, we can detect any light that's been coming to us since the universe was about 400,000 years old. And the way for us to detect that is to look at it in microwaves. Right now, the Europeans have launched the successor to the Wilkinson microwave anisotropy probe called the Planck satellite. It is sitting out about 1.5 million kilometers, about 1 million miles from the Earth, further away from the sun than the Earth. Taking data. We're hoping sometime in the next few weeks, actually, before the end of this course, that they will start to tell us what it's seeing. Is it seeing the same thing that the WMAP satellite saw? We hope so. We hope that it's not just seeing the same things that we understood, but also confirming the same mysteries, so that scientists like me will have lots of things and odd things to play with, and that I'll have lots of strange things to tell you about, not just this year, but next year. All right, so what have we learned? We've learned that the universe is very, very big. That it's not just big, but it's getting bigger. And it's getting colder. And since it's getting colder, it was once much hotter. And that's really fortunate because we're able to measure the glow of that early hot universe in the cosmic microwave background. And it tells us about all the things that we're going to learn about in the next 2 weeks. Dark matter and dark energy, and it's our window into the early universe.